Now, let's start looking at the theory of gravity. All right, we'll take a spherically symmetric source, meaning that the density is spherically symmetric, and therefore the shape. I'm going to be outside and not inside. I'm going to be in vacuum. Afterwards, I'm going to specify that we're talking about a local theory. So the source term in my field equation inside the mass could have a density, outside the mass it could be zero. I'm going to need to match boundary conditions and so on. It's spherically symmetric, right? At every point in space, there is a specific number telling you what the acceleration is. If you have particles moving with all kinds of different velocities in different directions, every single one will have exactly the same acceleration at this point. Correct? Is that true about any other force? Can you do this with any other force? No. Because what you have for other forces is exactly that, a force. You don't have an acceleration, you have a force. To find out the acceleration, you might need the mass-charge ratio and all kinds of other things. It might be velocity-dependent, etc. Only for gravity. So for gravity, we can define an acceleration field, which right away, even if we didn't do anything more, that's a beautiful idea. Okay? And it makes it very intuitive that all these particles will have exactly the same acceleration. Now, before we saw what is acceleration from the space-time perspective? It's equal to
Curvature.
worldline curvature. So we can, if we want, talk about a worldline curvature field. We didn't gain anything, it's just kind of a nice idea. At every point outside this mass, there's a worldline curvature field. Pardon me?
How do you assign the acceleration field for the space-time?
Okay, the acceleration field is really in space, but if it's a static source, all right, then I can just take it at any one time and it's representative at all times.
So it's the same for...
Right, I can draw the world line of the particle. I just take a, I know its acceleration at any point, I know its velocity at any point, I'll just draw its world line, whatever it is in a space-time diagram. Nothing is changing with time, so I can talk about a region of space just as easily as I can talk about a region of space-time. But the thing that we're interested in, the creature of interest, lives in space-time. It's the world line. Okay? Any particle whose world line is at that part of their world line, so to speak, is at that point, will acquire a curvature given by this specific event. All right? This acceleration field, which is really a worldline curvature field. And gravity is represented as an acceleration field. Okay? Now, we know that that acceleration really is a measure of what? The worldline curvature. Right? So really what we have is a worldline curvature field. That's really nice. Okay? So we have a field outside the mass. At every point in space, we have a worldline curvature field. Now, I have not left Newtonian physics when I say that. We can go one step further and talk, instead about the acceleration, we can now talk about the worldline curvature. And we can say, what is gravity? It's a theory of worldline curvature. Outside a spherically symmetric mass, you have a field of worldline curvature. And any particle crossing a particular point, no matter what their initial conditions, no matter their mass, has the same worldline curvature as a result of this field. So we can now recast this, instead of calling it acceleration, I can maybe give it some kind of a symbol, worldline curvature. I'll call it this, gamma. All right? So I can now say gamma equals gm over r squared. This is my worldline curvature field. Okay? And again, this is totally Newtonian. I didn't talk about anything that is not purely Newtonian and Newtonian gravity. In the Newtonian gravity naive space-time, where we have just worldline curvature and ordinary flat, space-time, whatever, I'll represent it as this. There's no real quantity like that. There's no such thing. This is exactly the worldline curvature. This is the acceleration. Just that it's kind of an undefined quantity, because really there should be an acceleration which is a vector. Maybe it's only in the r direction. This doesn't look like a vector. Whatever. It's just a symbol. It's not like the RT component of something. This is just a symbol. A, I know, is a worldline curvature, so I'm labeling it as gamma RT.